In this lesson, we will look at applications of antiderivatives. Earlier, when we looked at integrals of complex valued functions over contours, we looked at an example where two contours started and stopped at the same point, but the value of the integral was different along the different paths. So now we're going to investigate functions whose contour integrals are independent of the path chosen as long as the two paths start and stop at the same point. So to do this, we're going to first define an antiderivative. So an antiderivative of a continuous function f in a domain capital D is another function, and we're going to use capital F to denote the antiderivative, such that the derivative of f at z equals little f of z for all z in the domain. So a antiderivative of continuous function is a function capital F whose derivative is equal to f. So note that since capital F is differentiable, f must be analytic in the domain D. And further, every antiderivative of little f is unique up to a constant. So every antiderivative is equivalent up to a constant. So imagine we had two antiderivatives, f and g. We could define the function capital F minus capital G, and the derivative of this function would be equal to 0 since they're both antiderivatives of little f. This would just be f of z minus f of z. So any function whose derivative is 0 on a domain is constant. And so that shows that any two antiderivatives would differ by at most a constant. Our next theorem will be useful in determining when integration is independent of path and when an integral around a closed path has value 0. So for a theorem, we're going to suppose f is continuous on a domain D. Then there's three statements that are all equivalent to each other. So then the following are equivalent. In other words, the following three statements are either always true or none of them are true. First, f of z has an antiderivative capital F of z in D. Statement 2 says that integration of f along a path in D is independent of the path. So the integrals of f of z along contours lying in D from a fixed point C1 to another fixed point z2, these integrals all have the same value. And using the antiderivative of statement 1, we can define this value. So the integral of f dz from z1 to z2, using the antiderivative, it would be capital F of z2 minus capital F of z1, again where capital F is the antiderivative from part 1. And the third equivalent statement would be that integrals of f around closed contours line and D all have value 0. So if the second statement is true, then a closed contour, you can think of it as an integral from z1 to z1 for any point z1 on the closed contour. And so capital F of z1 minus capital F of z1 would always equal 0. So it's important to note that we are not claiming that any of these statements are true for a given function little f. So this theorem establishes the fact that either all of these are true or none of them are true. Now for the proof of this theorem, we're going to show that if 1 is true, then 2 is true, and if 2 is true, then 3 is true, and then go in the reverse. So we're going to assume if 3 is true, then 2 is true, and if 2 is true, then 1 is true. So that's going to be the outline of this proof. So we're going to show 1 implies 2, which implies 3, which implies 2, which implies 1. And so this establishes the fact that all these statements are equivalent. So first, we're going to show that 1 implies 2. That is, we're going to assume that f has an antiderivative, and then show that the integration along a path in D is independent of the path chosen. So let capital F be an antiderivative of little f, and let C be a smooth arc from Z1 to Z2, lying entirely in D. And the integral from Z1 to Z2 of f of z dz will be equal to the evaluation of the antiderivative of capital F at z2 minus capital F of z1. And since this value only depends on the beginning and end point, it is independent of path. So this integral's value is independent of path. So this is statement 2. Now we're going to assume that statement 2 implies statement 3. So we're going to assume that we have a closed contour in D that contains points Z1 and Z2, And we're going to assume that the integral along any path from z1 to z2 is equal. So let C be a closed contour and D containing 2 points z1 and z2. Then I'm going to break up C into 2 paths. So the paths are going to be C1 and C2. So C1 starts at Z1 and goes to Z2, and C2 also starts at Z1 and goes to Z2. So I'm going to write C as C1 minus C2. So C1 and C2 both start at Z1 and end at Z2. So C1 would go from Z1 to Z2, and then minus C2 would go from Z2 back to Z1. So we have this closed contour, C. Then, since C1 and C2 start and stop at the same point, the contour integral of f along each of those paths are equal. So then we're going to write the integral of f over C as the integral of f over C1 minus the integral of f over C2. But since we're assuming that both of these integrals are equal by statement 2, these integrals are the same, so when we subtract one from the other, we get 0. And that establishes statement 3. You see, when we had some contour over some domain D, and we have a point Z1 and a point Z2 in this domain, and you have any closed contour that contains those 2 points. So you could have any contour that's closed from these 2 points, starting and stopping these 2 points. We call C1 this upper half here, and we call C2 the other half. And so the contour C will be C1 minus C2. So it will be C2 for traverse in the opposite direction. So we've just shown that 2 implies 3. Now for the next application, we're going to show that 3 implies 2. So that is, we're going to assume that the integrals of f around closed contours all have value 0, and use this to show that the contours from fixed point z1 to z2 all have the same value. Well, just as we did before, we're going to assume that, so let C1 and C2 be 2 paths in the domain D that start and stop at Z1 and Z2. Then we're going to define C as the closed contour C1 minus C2. And therefore, we're assuming that the integral of C is 0. The integral of f of z dz over the contour C is 0 by assumption. We're assuming that in statement 3. But this is going to be equal to the integral of f of z over C1 minus the integral of f of z dz over C2. But this implies that these integrals over C1 and C2 are equal. I add the integral of f over c2 to both sides of this equation, we get that integral of f over these two paths are equal. So integration over any path starting and stopping at the same point are independent of the path chosen. Finally, we need to show that statement 2 implies statement 1. So we're going to assume that integration is independent of path. So since integration is independent of path in D, I'm going to define a function as an integral. So we can define capital F of z equal to integral from z1 to z of f of s ds. So this function is well defined because if z1 is any point in D, then as long as we take a contour from starting at z1 and ending at the point z, then this integral will always have the same value. So this function is well defined. For any value of z in D. So we need to show that capital F is an antiderivative of little f, and that will establish statement 1. So then it suffices to show that the derivative of capital F equals little f for all z and d. That is, that capital F is an antiderivative of little f. So to do this, I'm going to let z plus delta z be any point in D other than z. Then the difference, capital F z plus delta z minus capital F of z, using the integral definition, this would be equal to integral from z1 to z plus delta z of f of s ds minus the integral of z1 to z of f of s ds. And by combining this into one integral, this equals the integral from z to z plus delta z of f of s ds. Since this value is independent of path, we can just assume the path of integration is the straight line segment from z to z plus delta z. So the idea is we're going to take the limit of this difference as over delta z and let delta z go to 0. So delta z is a small quantity, and so small that the line segment from z to z plus delta z should be contained in the domain D. So it's the straight line segment from z to z plus delta z. So we'll come back to this difference in a minute. But first, notice that the integral from z to z plus delta z of 1 ds, well, the antiderivative of 1 is s, when I evaluate this at z plus delta z minus evaluation at z, you'll just get z plus delta z minus z. So the z's would cancel and I just get delta z. So I'm establishing this fact so I can write delta z as an integral of from z to z plus delta z. Then we can write f we can write little f of z as f of z times 1 over delta z, so times delta z, and I'm going to write this as f of z times 1 over delta z. And now delta z, we established this fact, is equal to the integral from z to z plus delta z ds. And now I'm going to I'm going to move f of z inside the integral since it's a constant with respect to s. So this is 1 over delta z times integral from z to z plus delta z of f of z ds. So we're doing this also we can rewrite the difference quotient. Therefore, the difference quotient, capital F of z plus delta z minus capital F of z all over delta z. Let's remind ourselves of what this quantity equals. So we have this, we've already established that capital F of z plus delta z minus capital F of z equals the integral on the right. So this difference quotient minus little f of z, and we just rewrote little f of z as an integral. So we see that this quantity will equal 1 over delta z times the integral that we established on the last page, the integral from z to z plus delta z of f of s ds, but when I subtract the minus f of z, and I'll subtract this integral here, I can write this as f of s minus f of z ds. So what we're going to show is that as delta z goes to 0, this difference, this whole expression right here, will go to 0 as delta z goes to 0, and therefore the derivative of capital F will equal little f. Now we're going to use the fact that f is continuous. So since f is continuous at z in the domain D, for every epsilon greater than 0, there exists a delta greater than 0, such that the absolute value of f of s minus f of z will be less than epsilon whenever s is sufficiently close to z. So that's whenever the absolute value of s minus z is less than delta. So now, remember, we're taking the limit as delta z approaches 0, so we can choose the value of delta z so that z plus delta z is within distance delta of z. So choose z plus delta z close enough to z so that the distance from those 2 points, that is the distance, the absolute value of delta z, is less than delta. then the absolute value of this quantity above will be less than or equal to the absolute value of the integral on the right-hand side, and bringing the absolute value inside, this would be less than or equal to 1 over the absolute value of delta z times the integral from z to z plus delta z of the absolute value of f of s minus f of z ds, and the integrand, absolute value of f of s minus f of z, will be less than epsilon. So this expression will be strictly less than 1 over absolute value of delta z times epsilon, which is our m in the ML formula, and the length of the contour from z to z plus delta z is equal to the absolute value of delta z, as we assume the contour was just a straight line segment. So this is just equal to epsilon. So we show that no matter how small of a positive value of epsilon we choose, that this difference here will always be smaller than epsilon whenever delta z is sufficiently small. So therefore the limit as delta z approaches 0 of this quantity is 0. So therefore we establish that the limit as delta z approaches 0, capital F of z plus delta z minus capital F of z over dz, this limit equals little f of z. And that's exactly what we want to establish. The fact that the derivative of capital F equals little f. So this establishes statement 1. So this concludes our theorem. We've shown that all or none of these statements are true. That is, they are all equivalent. If f has an antiderivative, capital F, then the integral of f along contours line and D all have the same value, and integrals of f around closed contours line and D all have value 0. So let's look at an application of this theorem. So suppose I have a contour C, which is the circle centered at the origin with radius 2. So this is the contour C, and C is given by the parameterization z of theta equals 2 e to the I theta for theta between 0 and 2 pi. Okay, so this is our contour, and I want to evaluate the integral over this contour of 1 over z, so dz over z. Instead of using this parameterization, I'm going to use antiderivatives. Now, we know that the log function, if we take a branch of the log function, its derivative will equal 1 over z. However, the antiderivative log of z is not defined and is not differentiable along its branch cut. And the branch cut would pass through this contour C. So what I'm going to actually do is break up C into left and right halves. So first I'm going to let C be C1 plus C2, where C1 is given by the parameterization z equals 2 e to the I theta for theta between negative pi over 2 and pi over 2. So in other words, the right half of this contour C. And I'm going to let C2 be given by the parameterization z equals 2 e to the I theta for theta between pi over 2 and 3 pi over 2. So what we'll see is that along C1, we can use a branch of log that has a branch cut on the negative real axis. And so 1 over z has an antiderivative on this contour. And then the same thing for C2, we're going to write C2 this way, and then we're going to use a different branch of log function that has its branch cut on the positive real axis. We're going to split up the integral over c into the integrals over c1 and c2 and use two different antiderivatives. So let's now evaluate the integral of 1 over z over the contour c1. So on c1, the principal branch of the log function, log of z equal to the natural log of r plus I theta, where theta is between negative pi and pi. This branch of the log function is an antiderivative of 1 over z. And this function is continuous and differentiable on the contour C1. So then the integral of 1 over z on the contour C1 would be equal to the antiderivative log of z evaluated at the starting and stopping point. So this contour goes from negative 2i to 2i, so I get principal log of 2i minus log of minus 2i, and when we evaluate this, this works out to the natural log of 2 plus the I times the argument of 2i, which is pi over 2. This is the evaluation of log of 2i for the principal branch minus natural log of 2 minus I times pi over 2. So the argument of negative 2i would be negative pi over 2. And so when we combine these, we get pi I. Likewise, when we look at contour C2, we can take the branch of the logarithm defined by log of z equal to n of r plus I theta, where theta is now between 0 and 2 pi. So this branch will have a branch cut along the positive real axis, so therefore this function is defined and continuous and differentiable. This function is an antiderivative of 1 over z as well. The integral over c2 of 1 over z is equal to this log function evaluated at the starting and stopping points again. This contour starts up at 2i and goes down to negative 2i. So we get log of minus 2i minus log of 2i. And for this branch of log, this will equal the natural log of 2 plus, now the argument will be 3 pi over 2 minus the natural log of 2 pi I over 2. So the argument of 2i is still pi over 2. And then when we simplify this, we get pi I. So then putting this all together, we have that the integral 1 over z over the contour c is the integral over c1 plus the integral over c2, and we get pi I plus pi I, which equals 2 pi I.